Nonlinear diagnostics can be activated from the Details window of the Solution Information tab. Details window of the Solution Information branch has two tables. First is Solution Information, and the second is FE Connection Visibility. All the nonlinear diagnostics parameters can be activated and listed from the Solution Information table. If we click on the drop-down next to the Solution Output tab of the Solution Information table, a list of options are displayed. We can choose the appropriate option to get more information about the solution in progress. Many nonlinear simulations involve large deformations and strains. This is frequently seen in hyperelastic, elastoplastic, or viscoplastic material simulations. In these simulations, elements are often strained so much that element shapes significantly change. Highly distorted elements cause problems in the FE model solution. It is possible to identify these elements using element violations. It is also possible to locate the elements that show very high residual forces. Identification of element violations, or elements with high residuals, helps to take a corrective action in the local region. In order to locate these elements, an appropriate number needs to be specified in front of the Newton-Raphson residuals and the element violations tabs. The number specified in these tabs indicates the number of recent iterations for which the element violations, or the elements with high residuals, are to be plotted. For example, 2 is specified in front of the Newton-Raphson residuals. Therefore, the Newton-Raphson residuals of the 2 most recent iterations will be displayed. Similarly, 3 is specified in front of the element violations. Therefore, element violations in the 3 most recent iterations will be displayed. These elements may change during every iteration. Therefore, only the most recent iteration outputs are retained, while previous iterations' information is overwritten. If we request Newton-Raphson residuals for the 2 most recent iterations, additional 2 branches will be added below the Solution Information branch. These branches will have names Newton-Raphson residual force, followed by the iteration number from the most recent iteration. If we click on this branch, Newton-Raphson residual forces will be plotted for this specific iteration. Elements with large residuals are shown in red color. In Details window, all the relevant information regarding these elements is shown. This includes load step number, substep number, iteration number, maximum residual force, minimum residual force, force convergence value, and force convergence criteria. The elements with the highest residual forces will be generally the elements causing solution problems. These are the elements where the difference in the actual stiffness of the structure and the assumed stiffness of the structure is very large. These elements can be eliminated by 1. Remeshing the structure in the local region. 2. Applying load more gradually by increasing the number of substeps. And 3. Making local changes in the boundary conditions. For example, a load or a displacement applied to a single node or vertex is more likely to cause a high residual problem. If such a load or displacement is applied to a small surface in the region, residuals are more likely to be smaller. We saw how to plot the elements with high Newton-Raphson residuals. Similarly, we can plot the elements with high distortions. If we request element violations for the last 3 iterations, a number of branches will be added below the solution information branch. Each branch will highlight the highly distorted elements. These branches include elements that violate the quality criteria, elements that have nodes with near zero pivots, elements that violate the volumetric compatibility, and elements with very high plastic strain. One branch is shown for each iteration. Thus, if we request element violation for 3 iterations, 3 branches will be shown for each of the above-mentioned types of element violations. The figure shows elements with large distortion. Once these elements are identified, local correction can be applied. Some of the ways of correcting the high element distortion problem are: 1. Remeshing the structure in the local region. 2. Applying load more gradually by increasing the number of substeps. 3. Using higher order elements. 4. Making local changes in the boundary conditions. For example, a load or a displacement applied to a single node or vertex is more likely to cause an element distortion problem. If such a load or displacement is applied to a smaller surface in the region, distortions are more likely to get distributed. 5. Using arc length method. 6. Using stabilization and damping. 7. Using nonlinear adaptive region. And 8. Deleting unwanted, highly distorted elements. We will go through some of the above-mentioned techniques in the subsequent modules.